Hello, welcome to this video. In this video, we will take one more problem on steady flow energy equation or a problem on first law of thermodynamics for an open system. So, let us start. Air flows steadily. So, steadily means a hint that it is a steady flow device. Air flows steadily at the rate of 0.5 kg per second. So, mass flow rate is given 0.5 kg per second through an air compressor. So, this device is an air compressor. If you want to represent it like a schematic diagram, yes, you can do air compressor which has an inlet and which has an outlet. Generally, air compressor volume is reduced, so it is decreased volume from inlet to outlet. So, this we always call it as 1 inlet and this as 2. So, air flows steadily at mass flow rate of 0.5 kg per second, entering at a velocity V1 7 meter per second and 100 kilopascal pressure. So, P1 is 100 into 10 power 3 Newton per meter square. Volume is meter cube per kg. So, he is giving you specific volume V1, small V1 0.95 meter cube per kg. And leaving, so he is now giving the outlet values. So, leaving at 5 meter per second. So, V2 is 5 meter per second. P2 is 700 into 10 power 3 Newton per meter square and specific volume at the outlet is 0.19 meter cube per kg. The internal energy of the air leaving is, so he is talking about internal energy leaving, is 90 kilojoule per kg greater than that of the air entering. So, we can write this mathematically. Internal energy of the air leaving is U2 is U1 plus 90 kilojoule per kg. Okay. So, because the internal energy of the air leaving is 90 kilojoule per kg greater than that of the air entering, can be written like this, or you can also write it like U2 minus U1 can be written as 90 kilojoule per kg. So, directly internal energy is given, that too specific internal energy is given. Cooling water in the compressor jacket absorbs heat from the air at the rate of 58 kilowatt. This is very tricky here. Cooling water jacket will be running around the compressor. See, if you want to run a compressor, in order to reduce the amount of energy which is spent on compressing, it has to be cooled. So, in order to cool that, there will be a water jacket which runs around the compressor. So, this water absorbs heat, which in other words, air is rejecting heat to the water. So, in terms of air, Q is negative because heat is rejected from air, to water. So, that is 58 minus, very important, minus 58 into 10 power 3 watt. So, negative because heat is rejected from air to the water. The working fluid is air, alright. Then compute the rate of shaft work. So, he is asking you what is the work transfer in kilowatt and find the ratio of inlet diameter to outlet diameter, pipe diameter. So, these two has been asked. Now, the first step is we will write the steady flow energy equation. We will write the steady flow energy equation. Q minus W is equal to, start with this, Q minus W is equal to change in enthalpy plus change in kinetic energy plus change in potential energy. Okay. So, now this has to be multiplied with mass flow rate because on the left side we have it in watts. So, this also has to be multiplied with mass flow rate. Anyhow, the potential energy term is neglected here because Z1 and Z2 not given. The moment there is nothing about Z1 and Z2, it is assumed that the inlet and outlet are at the same level. Okay. So, Q is minus 58 into 10 power 3, okay, minus work transfer is what we want to calculate, rate of shaft work is asked, multiplied by mass, that is equal to mass 0.5 into H2 minus H1 plus 0.5 into change in kinetic energy is half into capital V2 square minus V1 square. Okay. V2 and V1 are given, but H2 and H1 will have to calculate. How do we calculate H2 and H1? Remember, H2 minus H1, H2 is U2 plus P2 V2 and H1 is U1 plus P1 V1. Okay. Now H is given by U plus PV. So same thing I have written it here. So this can be rewritten as U2 minus U1 plus P2 V2 minus P1 V1. Okay. Now U2 minus U1 is 90 kilojoule per kg, but 90 into 10 power 3 because I want to represent it in joule per kg, because this unit pressure multiplied by specific volume will be in joule per kg. Now P2 is 700 into 10 power 3 multiplied by V2 is 0.19 minus this P1 is 100 into 10 power 3 into V1 is 0.95. Okay. Now this can be solved. We will solve the second term, then we will add the first term. 700 into 10 power 3 into 0.19 minus 100 into 10 power 3 multiplied by 0.95. So that is 38,000, or we can write it as 38 into 10 power 3. So 38 into 10 power 3, and this was 90 into 10 power 3. We can add 90 plus 38, 128 into 10 power 3. So joule per kg, remember. So H2 minus H1 we have found it by this way. Now we will go back to this equation. Minus 58 into 10 power 3 minus 58 into 10 power 3 minus W is equal to 0.5 into 128 into 10 power 3 plus 0.5 into half into V2 square, that is 5 square, minus V1 square, that is 7 square. Now let us do this separate, then we will solve it. Okay. It is like 0.5 into 128 into 10 power 3, the first term, 64 into 10 power 3 or 64,000, 64 into 10 power 3 plus this term 0.5 into 1 by 2 into 5 square minus 7 square minus 6. So this will be minus 6. So let us solve this equation now in order to get the value of W. So I will put it straight away. The equation minus 58 into 10 power 3 minus the unknown is x here, so I will use alpha x. Now alpha equals 64 into 10 power 3 minus 6. Now we will solve it. Shift solve for x is equal to 0 and say this is minus 121. So answer is this minus 122 we can write. So W is equal to minus 122 into 10 power 3. Remember this is in watts. So if you want it in kilowatt, divided by 1000, this 1000 and 10 power 3 cancels out, you will remain with minus 122 kilowatt. So, this is our work transfer. It has to be negative. We can also give a comment negative because compressor. So, work supplied is always negative. In a compressor, we are supplying the work. So, obviously, the answer has to be negative. So, minus 122 kilowatt. Now, let us go to ratio of inlet pipe diameter to outlet pipe diameter. The second part of the question is ratio of inlet pipe diameter to outlet pipe diameter. So, in order to do that, we will have an equation which we call it as continuity equation. So, since this is a compressible fluid air, we will have to use rho A1 V1 is equal to rho A2 V2. So, this is what we call as continuity equation. So, whatever mass coming in is going out, that is what we mean. Okay. So, rho 1 we know that density is 1 by volume, that is specific volume. So, this can be further rewritten as A1 velocity 1 divided by specific volume, and here also A2 V2, this rho can be rewritten as specific volume 2. And we are interested in this ratio. So, A1 by A2 I will simplify. So, this will go here, you will have V2, V1 comes here, and this small V1 goes to the top here, and this V2 will be here. Now, we have all these values. V2, capital V2 is 5, velocity 1 is 7, and small V1 and small V2 0.95, 0.19, 0.95, 0.19, 0.19. So, five into 0.95 divided by 7 into 0.19, which is 3.57. And remember, what we have got is area ratio. Area is proportional to d square. So, in order to get the diameter ratio, this has to be d1 by d2 must be square root of 3.57. So, square root of 3.57 will give us the diameter ratio from inlet to outlet. 1.89 is good. So, 1.8. Thank you.